Let's start with a warning. The popular 0D to 10D ladder you see online mixes real math with storytelling. In physics, when we say extra dimensions in string theory, we usually mean extra spatial directions that are as real in the equations as left, right, or up, down. We just don't experience them because they may be curled up extremely small. So why do extra dimensions appear at all? In ordinary particle physics, we treat particles as points. String theory replaces that point with a tiny vibrating string. Different vibration patterns look like different particles. One mode behaves like an electron, another like a quark, and one special mode behaves like a graviton, the particle-like version of gravity. That's one of the reasons string theory became famous. It naturally includes gravity. But when you write down the equations for a quantum string, the math is picky. If you try to make the theory consistent, it only works in certain numbers of dimensions. For superstring theories, that number is 10 total. 9 dimensions of space plus 1 of time. Not because someone wanted it to be weird, but because otherwise, the equations develop inconsistencies and the theory breaks. Of course, we only see 3 large spatial dimensions. The standard escape hatch is compactification. The extra dimensions are wrapped up so tightly that at everyday scales, you can't move in them. A classic analogy is a garden hose. From far away, it looks like a 1D line. Up close, you notice it has a circular direction around it. If extra dimensions are tiny like that circle, most motion ignores them, and the world looks 3D. In real models, those hidden dimensions can be shaped in complicated ways, often described with geometry names like calabi-yau. The important point is not the specific shape, but the idea. Extra directions can exist in the math without being big, obvious portals you could step into. Now, here's where M-theory enters. In the 1980s and early 1990s, physicists discovered something awkward. There wasn't just one string theory. There were 5 consistent superstring theories, each with its own rules. They're usually listed as type 1, type IIA, type IIB, and 2 heterotic versions. That sounds like a problem, because the dream was one theory of everything, not 5. Then a surprise. Many of these theories are connected by dualities. A duality is like a translation between 2 descriptions that look different but secretly describe the same physics. Sometimes it swaps small and large length scales. Sometimes it swaps strong coupling and weak coupling, meaning a theory that looks impossible to calculate in one form becomes easier in another. The biggest twist came from type IIA, string theory. When you crank up its coupling strength, the math suggests a new spatial dimension effectively opens up. More precisely, it behaves like there's an extra circular dimension whose radius grows as the coupling gets stronger. In that strong coupling limit, the theory looks 11-dimensional, and its low-energy approximation is called 11D supergravity. That unifying 11-dimensional framework is what people call M-theory. M has been joked to stand for membrane, mystery, or magic, but the core idea is simple. The 5-string theories aren't separate islands. They're different coastlines of a deeper theory. When you zoom out, you realize they're parts of one connected map. And this is where strings stop being the whole story. In M-theory, the fundamental objects include not only 1D strings, but also higher dimensional branes. The 2 celebrity examples are the M2 brane, a membrane, and the M5 brane, a 5-dimensional brane. In the string theory family, you also hear about d-branes, surfaces where open strings can end. Branes matter because they give you new ways to build particles and forces, and they help explain why the different string theories are related. One popular picture, heavily simplified, is the brane world idea. Our observable universe could be a 3D brane embedded in a higher dimensional space. Most standard model particles are stuck to the brane, while gravity can leak into the larger bulk. That's not confirmed, and it's not the only scenario, but it's a memorable way to visualize why extra dimensions might hide from us. So is M-theory proven? No. It's a powerful mathematical framework and a web of relationships that makes the whole string theory landscape feel less arbitrary. But we don't yet have direct experimental evidence for strings, branes, or extra compact dimensions. The scales where these effects become obvious might be far beyond what our accelerators can reach, and many versions of the theory can lead to different low-energy worlds depending on how the extra dimensions are compactified. The honest takeaway is this: M-theory is less a finished, final equation and more a big clue. It suggests that what look like 5 competing string theories might be different limits of one underlying structure, and that 11 dimensions can emerge naturally when you push the math into regimes where strings alone aren't enough. If your brain wants one anchor point, use this. In string theory, extra dimensions are part of the geometry of space. In M-theory, the story expands further. Strings are joined by branes, and an 11th dimension can appear when interactions get strong. If this helped, like the video, subscribe for more fast space breakdowns, and comment, does 11 dimensions sound like physics to you? or like sci-fi with better notation.